Alright, taking a look at 2014's Quiz 1 for Chem 351. The first question asks us to rank the dipole moment from smallest to largest, smallest being 1, largest being 4. Again here, we're going to think about things in 3 dimensions, and also think about the electronegativity of certain elements in these polar covalent bonds. So what I like to do in these rankings is find the worst, find the best. You see carbon fluorine, you think that's going to be great, but then you notice that, right, there's 4 of them, so they're all going to equally pull. So actually that's going to create no dipole moment. Polar bonds, but overall no dipole moment, so that's ranked the smallest dipole moment. And then from there you see 2 chlorines, 2 fluorines, and 1 chlorine. At this point I would say, well, 1 chlorine is not going to be as much as 2 or anything, so that'd be 2. And then you're comparing fluorine and chlorine, and fluorine's more electronegative, so I would say fluorine, would probably have the largest dipole moment. They're both pulling up this direction, but fluorine, because it's more electronegative, could pull a little bit more. The second one asks us to draw a Lewis dot structure for HNO3, show your work, and include all lone pairs and indicate the formal charges on all atoms. Biggest thing here, no charge, right? No charge, no net overall charge. You have nitrogen, so you should think about nitrogen saying nitrogen normally wants 3 bonds, but it's probably going to be the middle. The H usually wants to be bound to hydrogen. And the overall charge has to be neutral, so I start having nitrogen in the middle and have everything around it. Oxygen wants 2 bonds, so here oxygen has 2 bonds, here it has 2 bonds, and here it has a minus, and we keep track of our valence electrons. Overall, net neutral. Even though we have a plus and a minus, still net neutral, so we don't put a charge there. Hydrogen has 1 valence electrons, nitrogen has 5, oxygen has 3 or 6, and there's 3 of them, so that's 24. And then you start adding up, there should equal 24. So why does electronegativity decrease as you go down a period in the periodic table? Why is electronegativity? Because the atomic radius increases, right? Electrons getting farther from the nucleus containing positively charged protons, thus electronegativity decreases, right? They're getting farther from the electrons, and the valence electrons essentially feel the nucleus less because they're farther away. That's what changes. That's basically how we define electronegativity here. This other one, assign the hybridization state of each of the elements below, basically asking ourselves how many pi bonds does each thing have. This carbon here is sp3 hybridized, right? The hybrid state. Put a box around it, has no pi bonds. This one right here has 2 pi bonds, right? One with the nitrogen here, one with the nitrogen there. 2 pi bonds is sp hybridized. If you have just one, like this nitrogen has just 1 pi bond with the carbon, it's sp2 hybridized. So these hybrid states, right? Sp hybrid state aligns with having 2 pi bonds. So this carbon right here has a pi bond here and a pi bond here. So it must have 2 p orbitals. What's left over is forming these sigma bonds. And those are the sp orbitals. sp2 has 1 pi bond, right? So nitrogen 1 pi bond. And the rest left over are those sp2 orbitals forming the sigma bonds. And if you're sp3, right, you have no pi bonds, so you all molecular orbitals are basically the same. Alright, taking a look at the second part of the quiz here. Number 5, it says define the acids and bases on each side of the reaction below. What they're asking you here to basically do is, right, where is it electron deficient, what's electron rich? You can look at it 2 ways. Acids are, of course, electron deficient, bases are electron rich, but if you weren't sure on these, you could look over to your right and say, well, this has a negative charge, so that's a base. This has a positive charge, that's an acid. And on the other side would be the opposite, right? An acid, on the other side of the equilibrium arrow, has a conjugate base, right? It's lost a proton. And the base has gained a proton, so that's the acid on this side going back this direction. So it says, draw the structure of the expected conjugate acid, conjugate base in the following reaction. You're given the pKa's, that should be the key here. Low pKa means that's more likely to be an acid. High pKa means it's not. Also, you should just be able to look at this and say OH versus NH. An OH bond is much more polar. Oxygen is more electronegative than nitrogen. Nitrogen doesn't hold its lone pairs as tightly because it's not as electronegative as well. So those electrons are going to attack. You break the OH bond. Oxygen gets a lone pair, so now it's a negative charge. Nitrogen has used its lone pair to form a new NH bond, so now it has a plus charge. And so this would be the conjugate base, and this would be the conjugate acid. As you go down here, it says draw the expanded structure from the condensed formula below. A couple tricky things maybe, but looking at this, right, numbering your carbons out, 1, 2, 3, 4, 5, 6, 7, right? This is a carboxylic acid piece. You see the COOH. You see you have a CH2 in between there. Then also you have a CO, that indicates a ketone or carbonyl here. CH2, CH2. And then you see a CH here with a CH3 and a CH3 in the parentheses. And they're just one of those classic condensed expanded structure problems. Here, why is the alkyne CH acidic despite having a strong nonpolar sigma bond? So it goes back to, again, thinking about for a reaction to take place, what two things are possible? Either you have reactive starting materials, which in this case we're saying this is not a reactive starting material because that sp and the H have a pretty strong orbital overlap. sp orbital and that H have a strong orbital overlap, so it must be that this product must be very stable. So the product has a lone pair in an sp orbital. Now an sp orbital is the fat short one, which is close to the nucleus and the positive neutrons, which makes it more stable, right? Like dissolve or opposites attract. So putting electrons in an sp orbital is much more stable. Even though this is a really strong bond, it doesn't matter. If the product's really stable, that's a possible thing that could happen. The final one says draw the picture of electrons and bonds that explain the wave-like properties. You can show two waves coming together to make a bigger wave, that constructive interaction. Right? That's where we get the shading. The shading comes from, imagine like the top part of a wave. This is the bottom part of the wave below the sea level. But that doesn't mean where the electrons are at. It just shows you, right, that if two waves come together, right? So even these two bottom waves come together, you notice this part got bigger as well. So it's a constructive interaction. That's what we show these shading, which is really just phasing.